Hey Chemsters, this is Mrs. Vandalay bringing you another Chemster video. We're still on chapter 6. We're talking about IMFs. This is part 2, all right? So we just learned about the different kind of intermolecular forces of London dispersion and then dipole-dipole. Every single molecule will have London dispersion, so nonpolar molecules will only have London dispersion. We learned that polar molecules will have dipole-dipole. So problem number 4, it says which of the following will have dipole-dipole forces? Well, what's the first thing we need to do is draw each molecule. So why don't you literally pause this and do A, B, C, D, E, all right? Don't do this one, I've already done it for you, okay? And then go back, after you drew it, determine if it is polar. Remember what makes polar? Not symmetrical and polar bonds. So if it is symmetrical or you have polar bonds, then it is going to be nonpolar. Okay, so go ahead and pause this and see how you do. Okay, welcome back. I hope you actually did this. The more practice, the better you'll be. All right, and so here is CO2. And the problem with this one, this is nonpolar, so there is no dipole-dipole, only London dispersion because it's perfectly symmetrical. The next one is here. And what's happening? We have a polar molecule. Why? Because it is not symmetrical. I have 2 hydrogens and 2 chlorines, not symmetrical. And this right here and this right here are polar bonds. So yes, this is a polar molecule with dipole-dipole and London dispersion, but your stronger is going to be dipole-dipole. Well, it's cousins right here. And the only difference between B and C is that there's chlorines here and only hydrogens here. So this is nonpolar. It is perfectly symmetrical, so we'll only have London dispersion. Letter D is up here. Hopefully that wasn't too hard. And this is not symmetrical. And it has a polar bond right here, polar bond, so it's dipole-dipole. It has London dispersion too, but the stronger one is dipole-dipole. And finally, here is CH2O. It is not symmetrical, and right here is your polar bond. Therefore, it is a polar molecule with dipole-dipole. All right, so what's my final result here? All right, so we said this is nonpolar that has only London dispersion. We said this is polar because of the chlorine, so it has London dispersion and dipole-dipole. We said this one is nonpolar because it's perfectly symmetrical, so it only has London dispersion. HCl has both London dispersion and dipole-dipole, so it's polar there. This one's polar, it has London dispersion and dipole-dipole. So what about this one? Is it symmetrical? No. Do you see some highly electronegative elements, the NO, F, or Cl? And the answer is yes, right here. So it is a polar molecule with London dispersion and dipole-dipole. Hopefully that helps. So what about the next one? This is the hydrogen bonding. All right, it is a super-de-duper case of dipole-dipole. It's like dipole-dipole on steroids. All right, and there is a special requirement for hydrogen bonding. They are polar molecules with nitrogen, oxygen, and fluorine attracted and attached actually to the hydrogen of, it has to have an H and an H and an O, an H and an F. The H has to be directly on the N, O, and F, all right? Not chlorine. Why would I not include chlorine? It's too big. So the big four, the 4 most electronegative elements are NOFCl, but hydrogen bonding does not include Cl. So this intermolecular bond strength is actually higher than other dipole-dipoles, and your examples will include water, probably the most common case of hydrogen bonding, alcohols, carboxylic acids, amines, amides. Those are organic compounds, and if you take organic chemistry with me next year, the year after, we talk a whole lot more about this, okay? So here's an example of hydrogen bonding. I guess you're using like HF. So an H bonds directly to F or N, so there's an H and an F, all right, or an H and an O, or an H and an N. So the H has to be on those 3 elements, or one of those 3 elements. The bonding atoms acquire relatively large partial charge, giving rise to very strong dipole-dipole attractions between neighboring. So it is, like I said, a super case of dipole-dipole, okay? Remember how I said structure determines function? Well, again, why is it so important that this hydrogen bonding even occurs? Well, let's look at water. Water has an extremely high melting and boiling point, has extremely high surface tension, and we saw that with your polar lab that you took home. Remember you counted how many drops of water went on that penny? That's because water has such high intermolecular attractions due to hydrogen bonding. If you put oil on water like that, you're going to have so fewer number of drops of oil because it doesn't have this kind of bonding. If you put gasoline on a penny, you're going to have much fewer drops than you did of water because gasoline and oil does not have this hydrogen bonds, okay? So look over here, you'll see the molar mass, because that's your London dispersions. That's when we talked about boiling point last time, is just about based on molar mass, and here's your boiling point. So take a look at this chart here. CH4, SiH4, these are all nonpolar. These only have London dispersion. All right, so when you look at some of these actually have about the same molar mass, but a little bit higher boiling point. These are also fairly nonpolar, if I remember right, but look at water. Water is a highly polar molecule. It has H directly attached to the O. Therefore, it has an extremely high boiling point compared to other things of like molar masses. CH4 has a molar mass of 18. So does water. So they have the same exact molar mass, but look at the huge difference between their boiling points. So what does this tell me? Water has a lot higher intermolecular attraction than does CH4. That's what that tells me, okay? Problem number 5 says draw ethanol and dimethyl ether. What do they have in common? All right, so here I have ethanol is a carbon with an OH, and dimethyl ether is a carbon-oxygen carbon. So what do they have in common? I, once again, because it's really messy, left off all the H's off the carbons. There's 3 H's here, 2 H's here. There's 3 H's here and 3 H's here. They have what's in common, the same molecular formula. They both have 2 carbons, 6 hydrogens, and 1 oxygen. Okay, so they have the same molar mass. That's what they have in common. Okay, what's different? Well, what does each one have as far as intermolecular force? Well, they all have London dispersion. This is a not symmetrical molecule, therefore it has dipole and a oxygen with a carbon and hydrogen, so I have a very electronegative element, so it also is dipole, but the H is directly attached to the O. So this one has all 3 types of intermolecular attraction, the hydrogen bonding being the strongest. Now dimethyl ether has always London dispersion, okay? It has dipole because this is not a linear molecule. If you remember, there's 2 lone pairs on oxygen, all right, making it bent. Therefore, there's a region of partial positive, partial negative on dimethyl ether, making it dipole. But is there a hydrogen directly attached to the oxygen? The answer is no. So this one has London dispersion and dipole. So one of these have a boiling point of -22 and the other one is 78. So which one is which? Okay. Think about it, and when you're done, come back. All right, well, I said dimethyl ether is -22 and ethanol is 78. Why? Because of the hydrogen bonding. All right, the hydrogen bonding makes those molecules much more attracted to one another, so that it takes a whole lot more energy, as in temperature, you know, to separate the molecules and become a gas. This one is typically it is a gas at room temperature, and that's what the early anesthesia it was made out of, was dimethyl ether. Actually, I think it was diethyl ether, one of the two. So anyway, I hope that answers that. So, which substance has the highest boiling point? Well, I kind of gave you already the kind of intermolecular forces. This one has hydrogen bonding as its strongest, OH. This one has a dipole as its strongest because it has a C and an O and it's not symmetrical, it's polar. And CH4 only has London dispersion. All right, so what will then have the highest boiling point? Which one did you say? I hope you said this one right here. This is your methanol, this is your alcohol, and so it does. All right, so problem number 7, why don't we get that set? I'm going to do 2 of these from this chart, and I would like you to finish this chart for homework, okay? So the Lewis structure, what I'd like you to do is actually do number 1, this one right here, and when you are done filling out this chart, come back and then we'll go over it, okay? So do that first, I mean it, and then we'll check it. Okay, hopefully you finished it and not waiting for me to do it for you. That's not very helpful. Hopefully you got the Lewis structure. You've seen this a lot. It is linear. Why is it linear? Well, the coordination number for carbon is 2 with no lone pairs. It makes it sp hybridization, therefore it must be linear. Is it a polar molecule? The answer is no. Why not? It is perfectly symmetrical. All right. Therefore, the strength, the action pulling the electrons closer to it cancel each other out. Their vectors cancel, if you remember the last time. So what kind of force does it have? Only London dispersion. Do I have any diagrams? No, I have no diagrams to show you because it's London dispersion only. If this is dipole-dipole or hydrogen bonding, then yes, you need to show the diagram. What I would like you to do next is HF. Go ahead and do HF right now, and then when you're done, come back, okay? All right, hopefully you did it, and that you're not just watching me do it. Here's HF, okay? Fluorine is my central atom. Its hybridization is sp3. Why? It has 1 bond and 3 lone pairs, adds up to 4. Coordination number is 4, but with 3 lone pairs, it is linear. All right. Is it polar? Yes. How do I know? It is not symmetrical, and I know this bond is a polar bond. 4.0 minus 2.1 is like 1.9 even. All right. So it's so polar, it might be ionic. All right, so what about the forces? It has all 3 of them. It has London dispersion. Every single one of these are going to have London dispersion. It also has dipole-dipole because it is polar, and it has hydrogen bonding because the H is on the F. Okay, so diagram showing, this is what I want you to do. Put 2 molecules, right? Because dipole tells me 2 molecules with 2 poles, okay? So I know fluorine is electronegative. Therefore, it's partial negative. Hydrogen is going to be partial positive. So I'm going to put both of these here. So now what? What is the force that I want you to show? Well, here's where your attraction is, all right? The fluorine is attracted to the hydrogen of the other compound, and that's what hydrogen bonding is all about. So what I'd like you to do now is do the rest of the page, all right? And guess what we're going to do when you come back? We're going to go over it. So don't wait to be great. We'll see you next time. Take care. Bye-bye.